Okay, so in this question, we've got part A involves using the equations of motion. So this small object of mass 0.02 kilograms is dropped from top of a building 160 meters high. So part A says, ignoring air resistance, calculate the speed of the object as it hits the ground. So because it's dropped from rest, okay, we know that U is 0, right? The initial speed. Drop from rest, U is 0. And when it hits the ground, it would have travelled 160 meters. So we can set S to be 160, all right? And notice also, because it's been dropped and it's going downwards, right? I'm taking downwards as positive, all right? So 0 displacement here, and then displacement increases as it goes down, because downwards positive, so plus 160. We know acceleration is 9.8, and this time we're going to write positive 9.8 because downwards is positive in terms of what I've defined, and we've got gravity sort of going in that downwards positive direction. So then we want to find V, don't we? Okay, so that's what we were looking for. So we'll use V squared equals U squared plus 2AS. All right, so then U is 0. Plus 2 times 9.8 times S, which is 160. So we get 3136 for V squared, and then to get V, we square root it, and we get 56 meters per second exactly. Okay, so that's the velocity when it hits the ground. Part 2 then, it says the time taken for the object to reach the ground. Okay, so as we want T, okay, remembering that we know U is 0, we know S is 160, we know A is 9.8, so we could use S equals UT plus half AT squared. Okay, so then when it hits the ground, it'll be 160. U is 0, so that cancels that out there, and we'll have half times 9.8 times T squared. Okay, so it'll be 160 equals 4.9 T squared, and then to get T, of course, you've got to divide by 4.9, and then you've got to square root that. So square root 160 over 4.9, and we get 40 over 7. Okay, notice that I've taken the positive root when you square root plus or minus, but we'll take positive there, we won't even bother write plus or minus because we know we can't have minus time. So 40 over 7, I'm going to leave it like that because it's quite nice, leave it as a fraction. As a decimal, it's repeating 1. So part B then, right, we go on to now part B where we're using Newton's second law, right? We introduce Newton's second law, and if we look at what we've got here, back to our picture, it says now in part B, it says assuming the air resistance has a magnitude of 0.096. So if we see our diagram, right, it would be better if I draw it again. So we've got this object falling, haven't we? Right, and we're going to label the weight. Okay, because we need to label all the forces, and the weight of the object is what's making it fall, right? So the weight is just the mass, which is 0.02 times gravity, okay, times the g value, which is 9.8. Okay, but we write it as that. We write it as 0.02 g. Okay, that's how we write the weight, the mass times gravity, value of gravity. Now it's got a resistance. It says resistance of 0.096. In other words, something slowing it down. Okay, so something pushing it back up. So when it's falling, there's something stopping it fall so rapidly. Maybe air resistance. Okay, so that's sort of like almost like pushing it back up. So we've got a force going upwards in the opposite process, 0.096. Okay, and it says then find the magnitude of the acceleration of the object. Now because it's going down, we put the direction of acceleration going that way. Right? And this time the acceleration of the object isn't going to be 9.8. Okay, right? In the last question, part part A rather of this question, part A, acceleration was 9.8, wasn't it? Because it was falling freely under gravity. Okay, this object was falling under gravity, so the acceleration was 9.8, and we ignored any resistances. We assumed they weren't there. But if we bring in the resistance, if we assume there is a resistance, something that's actually slowing it down, the acceleration won't be 9.8 anymore. Okay, it won't just be the gravity that's affecting it. Okay, you've got this resistance stopping it fall so rapidly. So the acceleration, we don't know what it is, we'll just call it A. Alright, so if we then use Newton's second law, okay, Newton's second law, and that will be then in the direction of motion, okay, in terms of which way it's going, so it's going down. So it's going down, that means this force has got to be greater than this force, yeah? So if you think about it, when there's two forces pulling on an object, okay, the direction it's going in means that that force pulling in that direction has the greatest effect, doesn't it? So this weight of the object is obviously greater than the resistance, because it just keeps falling. So seeing as that's the greater one, to get the resultant force, we'll have this force here, but then of course we've got to take away the resistances so it doesn't have such an effect. Okay, so we've got this overall weight here, but then taking away the resistant force to get my overall resultant force here, and that will equal mass times acceleration, and the mass is 0.02 times the acceleration, which of course is A, and then all we've got to do is plug these numbers into a calculator, and remember G is 9.8. We'll work that out. So that comes to be 0.1, because 0.02 times A. So then to get A, we just take the 0.02 over and divide, okay? And we get 5 meters per second squared, okay?